Lipophagy, the autophagic breakdown of lipid droplets within cells, is a critical process in maintaining lipid balance and overall metabolic health. Unlike the passive storage of fat, lipophagy represents an active, regulated mechanism through which cells manage their internal fat content by targeting lipid droplets for degradation in lysosomes. This selective form of autophagy allows the cell to convert stored triglycerides into free fatty acids that can be used as fuel during periods of energy demand, such as fasting, exercise, or metabolic stress. It serves not only as a source of energy but also as a protective mechanism to prevent the toxic buildup of lipids that can disrupt cellular functions. In healthy metabolic conditions, lipophagy plays a quiet but essential role in keeping intracellular fat at manageable levels. When a cell senses that energy is needed, lipophagy is activated to release fatty acids in a controlled manner. These fatty acids are then transported to mitochondria, where they're oxidized to generate ADP, the cellular energy currency. This process allows for metabolic flexibility, the ability to switch between fuel sources, which is a hallmark of a healthy, responsive metabolism. Furthermore, lipophagy is tightly integrated with mitochondrial quality control. As lipid breakdown occurs, the process often coincides with mitophagy, the removal of damaged mitochondria, thus ensuring that energy production is both efficient and safe. The positive implications of a well-functioning lipophagic system are wide-ranging. In the liver, for example, lipophagy helps prevent the development of fatty liver disease by clearing excess lipid droplets from hepatocytes. In muscle cells, it supports endurance and energy efficiency. Even in immune cells and neurons, lipophagy contributes to cellular resilience and balanced inflammatory signaling by keeping lipid composition in check. This points to its importance not only in energy management, but in protecting organ function across systems. However, a breakdown in lipophagy is increasingly observed in individuals with obesity. In these cases, the machinery responsible for identifying and transporting lipid droplets to lysosomes becomes less efficient. Cells become overwhelmed with excess fat, which accumulates in an unregulated way. This unchecked lipid buildup not only disrupts cellular signaling but also contributes to chronic inflammation, insulin resistance, and organ dysfunction. In the liver, reduced lipophagy is associated with the onset and progression of non-alcoholic fatty liver disease, NAFLD, a condition now common in both adults and children living with obesity. In adipose tissue, the loss of lipophagic activity can cause fat cells to swell uncontrollably, leading to impaired secretion of key hormones like adiponectin, which helps regulate glucose and fat metabolism. Despite these concerns, there is strong evidence that lipophagy is a reversible process, and this opens up a powerful therapeutic window. Lifestyle interventions such as intermittent fasting, caloric restriction, and aerobic exercise have all been shown to restore or enhance lipophagic activity. These natural stimuli trigger nutrient-sensing pathways that re-engage the cell's autophagic machinery, allowing for the safe mobilization and clearance of excess fat stores. Certain bioactive compounds found in foods, such as polyphenol from green tea or resveratrol from red grapes, may also stimulate lipophagy by activating cellular stress response systems like AMPK or sirtuins. Even more promising are emerging pharmacological approaches aimed at specifically targeting lipophagy in metabolic organs, offering potential treatments for obesity-related complications without the side effects of blunt fat-reducing strategies. It is worth emphasizing that lipophagy is not about the elimination of fat, but about fat management. It enables the body to treat fat not as a static storage depot, but as a dynamic energy reserve that can be mobilized when needed and regulated when in excess. This distinction is critical because it suggests that metabolic health does not depend solely on how much fat a person has, but on how well that fat is handled at the cellular level. Restoring lipophagy may thus improve health outcomes even in individuals who remain overweight by enhancing the metabolic function of their tissues. In conclusion, lipophagy is a cornerstone of lipid regulation and cellular energy balance. While it is often suppressed in the setting of obesity, it remains highly responsive to targeted lifestyle and therapeutic interventions. Its restoration could play a key role in reversing the cellular lipid overload that drives many chronic diseases today. Far from being a passive background process, lipophagy is a dynamic and potentially transformative force in the body's effort to maintain metabolic homeostasis, and its promotion represents one of the most promising strategies for long-term health and disease prevention.